typically has an initial value, and there might need to be more than one, as we'll talk about that in a moment, and a rule for generating new values given previous values. So here's an example of a recurrence relation that's pretty basic. We could look at x, the initial term x of 0 is equal to 3. And then we could say if you have the next term, in other words, the n plus first term, you just get that by adding 5 to the previous term. So I can use this rule to generate terms of this sequence concurrently, or consecutively. I would start out with x sub 0 equals 3. X sub 1 is going to be the previous term. Add 5 to get the next term. So x sub 1 would be 8. X sub 2 would be 8 plus 5, which is 13. X sub 3 would be 13 plus 5, which is 18. And I can continue this for as long as I want. However, I keep having to generate terms. And what I can't do just based off a recurrence relationship is ask, what is x sub 200? Well, if all I have is this recurrence relation, I'm going to have to generate all 200 values. I'm going to generate up to the 199th value and then add 5. So this is difficult to answer with it takes time to answer if you're given a recurrence relation, but it's much faster to answer if you are, but it's much faster if you have a formula. So if you look at this, here's the recurrence form of this, but there's also a closed form expression for this one, which is that if you look at this, you have 3 plus 5, and you've added 5 however many terms you're in. So this is 3 plus 5 times n. And so now, if you want to generate the 200th term, you don't have to generate the first 199 term. You could just go straight to x sub 200 is equal to 3 plus 5 times 200. So x sub 200 would be equal to 1003. And that because you had this closed form expression, you could just plug in the value of n. So another way that another example that you might see for a recurrence relation is you might see something like y sub 0 is equal to 2 and y sub n plus 1 is equal to 3 times y sub n. And so we could look at the same situation where we're generating terms, and this is the recurrence relation form. And we can see if we can recognize what the closed form expression would be. So y sub 0 is 2, that's given. Y sub 1 is equal to 3 times 2, which is 6. Now let's go ahead and look at y sub 2, but let's look at it not as 3 times 6, but as 3 times 3 times 2. This is a case where simplification is actually your enemy, because when you simplify, it can obscure the pattern of what's happening. To get y sub 3, I multiply 3 by y sub 2, the previous term, and that becomes 3 times 3 times 3 times 2. So notice that I have 3 3's multiplied together, and I'm on y sub 3, and this is equal to 54. And then if I look at y sub 4, I have 3 times y sub 3, which is going to be 3 times this whole thing, which is 3 times 3 times 3 times 2. So that becomes 3 to the 4th times 2, which is 162. Here's the thing, you want to find this pattern, and finding this pattern, you get that y sub n is equal to 2 times 3 to the n. Because if you look back at each of these, I'm multiplying 3, matching the subscript on the expression. So this would be my closed form solution. My closed form solution makes it much easier to recognize that this is an exponential and to evaluate specific values if I wanted to. And figuring out closed form expressions from recurrence relations, a big enterprise in math. You're likely to see sequences in other classes, and either in this class or in other classes, that's something you'll probably learn. For now, let's just make sure that we understand that you can define a sequence by a recurrence relation. And that one of the goals you might have with that recurrence relation is to find a closed form expression gives the same values as the recurrence relation form.